in actual brain, neuron is a cell or the minimum computational unit within the brain, that is called a neuron, and it has several inputs, several thousand inputs, and only one output, which is given through the axon. But what actually mathematically it represents? Mathematically, a neuron is a, you can say, double capacitor, or you can say it is a two-dimensional integration. It integrates with respect to time and with respect to space also. So it adds temporal and spatial integration. So a neuron is a spatial and temporal integrator. So using a capacitor which is able to integrate the input signal with respect to time, that is integration of some function into dt, that is with integration with respect to time, and integration with respect to the space, because the number of connection, number of inputs coming to the neuron comes from different portions that is scattered in the space. So that's why two type of integrations are needed for designing or for making or for developing a neuron. But for solving some problems, some real problems in the science, we need a number of neurons within the networks. Sometimes maybe in millions. And if you see the brain of a single ant, it has about 25,000 neurons. 25,000 neurons, and the connections are much more than this number. So the smallest brain in the nature is having so many neurons. So if you try to make that brain within the computer, so you see how much the size of the memory will be needed, or how much the weights will be needed for solving the problem using the smallest brain even. In this figure, you see that in actual brain, the size of the computational element, that is the neuron, is very small, in nano range, and the voltage generated within the brain is of the order of, let's say, microvolt. But in case of your computers, the voltage generated is in the range of volts, high volt, let's say. So that's why, and the number of processors inside the computer is just 4 processors, that is quad processor, that has only 4 processors. But in the human brains, the number of processors are about 10 raised to power 11. So that's why there is parallel processing within the brain, and a simple computer cannot match the processing done by the brain. The brain takes energy for doing these calculations. But the main advantage of the brain is that because the voltage levels handled by the brain are very small, but the voltage levels handled by the normal computer are very high. So that's why the power needed or heat generated by the normal computer is very high as compared to the brain. So that's why if we try to simulate or make a brain in electronics, the size of the brain, the size of the chip, the size of the IC will be around, let's say, 20 kilometer or so. 20 kilometer by 20 kilometer by 20 kilometer. So much volume will be needed for making, for simulating the brain, if you try to simulate within a hardware. And the power needed for operating that brain will be, I think, in megawatts. So that's why it is not possible to make a brain which is just similar in capabilities of the natural brain. And the most important thing about the brain is that The frequency handled by the brain is very small. Normal computer, the clock frequency is in gigahertz, but in case of brains, it is only in hertz. For example, uh, when we are aware, when our brain is aware, the frequency generated within the brain is called gamma wave, and whose frequency is just greater than 30 hertz. And when we are alert, this frequency is called beta wave, and the range is 13 to 30 hertz only. And in case of when we are relaxed, the frequency is 8 to 12 hertz only, and this is our alpha wave. And when we feel tired, the frequency generated, the wave generated within the brain is theta wave, and the frequency is 4 to 7 hertz only. And when we sleep, the frequency generated within the brain, the wave generated within the brain is called delta wave, and its frequency is about 1 to 3 hertz only. So when we go towards calmness, the frequency, the wave generated within the brain goes to very low frequency. So in coma, it is again very, very low frequency. So that's why the total energy consumption by the brain decreases. On the other hand, the frequency used by the computer, normal computer, is 10 raised per 9 hertz, that is in gigahertz range. That's why it takes a lot of power. If we compare the power used, that is the energy used by the brain during different activities, so when we are idle, doing nothing, the power used by the brain is like 25 watt. But when we are driving, during driving, the brain uses about 90 to 100 watt power. So maximum power by the brain is used when we are driving. So that's why after a span of 1 hour or so, we are tired. Our brain, there will be some fatigue. Some fatigue will come within the brain working, and you may take some wrong decision during driving. So types of problems, we can use the artificial brains, or you can say the artificial networks, or you can say the neural networks. So for mathematical modeling, classification, clustering, forecasting, vector quantization, pattern association, control, and optimization. So these are the areas where we can employ the capabilities of the neural networks. Here vector quantization is, uh, in this we represent each entity using a vector. For example, if we want to compare two human beings or two human faces, then we represent the human beings using vectors. What type of vectors? For example, what is the nose size, what is the eye size, what is the angle of the eyebrow, what is the color, etc. So we take generally, let's say 10 to 15 vectors and represent using a vector. And then if you want to compare two persons, then we difference the two vectors and find out the distance between these two vectors. But you all know that Euclidean distance, which you generally study in physics, is not useful here, because Euclidean distance gives equal importance to each coordinate, each axis, but that is not useful in case of matching two persons. For example, if there is a difference of height of 1 centimeter in two persons, other things are similar. And in another context, if there is a difference of 1 centimeter in eye size in two persons, so in the first case, when the difference of height is 1 centimeter, and in another case, when the difference of eye size is 1 centimeter, these two persons will be totally different. That's why, but Euclidean distance will not actually provide with enough discrimination for differentiating these two persons. That's why Euclidean distance is not useful. So generally we employ other type of distances, for example Mahalanobis distance, which gives different type of weightage to different type of you can say axis. But how the brain learns, because if we know the process how the learns, only those principles we can employ are making the artificial network to learn. And the most important principle for learning in human brain is Hebbian learning. So you see here, what is actually Hebbian learning? In short, you can say Hebbian learning means fire together, wire together. The principle is fire together, wire together. It means when we apply some stimuli to the network or to the brain, the neurons which are triggered simultaneously at the same time. So those are wired permanently. So the principle says when we apply the input to a network, to a neural network, the neurons which are fired together. Fired means uh, which neurons generate output. Because when we disturb a neuron, it is not necessary that every neuron will feel disturbed. So it depends upon the total. Time it means they are connected. So similar logic is used in designing neural networks or in making to learn in case of neural networks. So we apply the stimuli, input stimuli, and see which are fired together, and then the weight of those connections is increased, which are fired simultaneously. So in this case, it is shown actually if these two are fired uh, together, so these are connected. So here another application where we can use these type of machine that the neural networks is the lip reading. We all know that when we speak, for example, when we say papa, or let's say when we say p, or when we say b, baba, p, papa, b, baba, in both cases the lips are closed. P, when we pronounce p, that is papa, the lips are closed. And when we pronounce b, that is baba, the lips are closed. When lips are closed, nothing will come out of the mouth. That is, no signal will come out from the mouth. If nothing is coming out of the mouth, then how the listener will know what the person is speaking? So, in the absence of signals, we cannot guess where the person is speaking. But generally, you see that we are able to guess what the person is saying, whether Papa or Baba. Actually, the clue is that whether a person is saying per or b depends upon the duration for which the lips are closed. So our brain is very much trained for listening sounds and seeing the figures. So it estimates the duration of the closure from the face, and from that it is able to guess the sound on phone when we talk, generally you can see that some people when say B, so he says B for Bombay, P for parrot, because the listener brain is not sometimes capable of understanding what the person on the other hand, other side of the phone or the network is saying. So in this case, we can design systems which are able to interpret the sound, interpret the speech, and those type of applications where this is very helpful is, for example, in case of blind people. So we use this type of science. So the speech is directly converted from the facial expressions to the audio form and given to the this listener, because the person is blind, so he is not able to read the lip or the emotion and shown by the face. So that's why we can use lip reading for this. And similarly, in medical science, the neural networks can also be used for developing very high accurately develop these figures, the bone figures or bone networks. The neural networks can be trained. What is the shape of the bones? What is the shape of the structure of the hand or leg or any part of the species we are investigating? So the images given by the X-ray are sent to the neural network and it applies its logic on the incoming image, and the output given by the neural network is very, very clear, because it removes all the undesired information, undesired disturbances from the image, and we at the output we get a very, very high quality image. And in future, we will be able to use both type of capabilities within the machine. Both type of capability means we will be able to develop hybrid intelligence. Hybrid intelligence means we will be able to take advantage of the capabilities of some particular animal and mix those capabilities to the capabilities of the machines, that is of the processors. And a hybrid processor can be made using the intelligence of the brain, real brain, and computational capabilities of the hardware. And for example, here, if you take the example of a honeybee, the honeybee has two eyes, and each eye is composed of about 5,000 small sections. And those small sections work independently. There are independent processors for each section. So that's why you can say honeybee has 5,000 eyes within one eye. So that's why it is able to estimate the polarization of light. So when it travels, it is able to guess the exact change in time, the exact change in the rays coming from the sun, the exact rays picked by its eyes, because and the orientation changed because of the, let's say, change in the air pressure, change in the air density, etc. Because if it is not able to do this type of processing, then you know that the flowers emit ultraviolet rays, and it reaches to the flowers because of the emission of the ultraviolet rays. It can easily see the ultraviolet rays, and it reaches to the flower. And reaching at an exact instant to the flower is very important, because honey is produced only for a very small time, let's say for 1 second. Continuously flower does not produce the honey, so that is a particular moment when the honey is produced. So that's why it should be, the honeybee should be very exact in reaching to the flower. Otherwise, that will be waste of time if it reaches there after 1 second or 2 seconds. So this type of scale of accuracy, it is able to get because of the parallel processing going on within its eye. That is 5,000 different sections per eye, and that comes because of the picking up the polarization of the light by the eye. So here in the figure also, for example, if a monkey is used for just for capturing its real brain, and then if its brain is mixed with the neural networks or another hardware, so whatever it thinks, that decision will be captured by the computer, and computer will take decision in accordance with the signals got from the brain of the monkey, and a robot will be directed to act like a monkey, we would say. So this type of hybrid processing will be very, very useful for the future wars. Why our soldiers should go to the war? Animals can go, honeybees can go and harm the enemies. So in future, these type of systems will be very common. So here also, the capabilities of the human brain can also be increased if we use hybrid intelligence. That is, if we compensate some of the capabilities of the human brain by hardware chip and by the capabilities of another brain, another insect brain, that you can say, so that the capability which we do not have, that can be gathered by just hybrid intelligence. So in image recognition, or you can say in face recognition, these networks are very, very useful if you see all these images, because what is the problem actually? Each image has very large number of pixels. If a image is, for example, 500 by 500 pixels, then multiply both. So million of pixels are required for representing a single image. So if there are millions of pixels in the image, then our processor will be busy in handling each of the pixels individually for estimating what is the image, what is the face in the image. So what actually we do, we first reduce the number of pixels inside the image by resizing the image or by converting the image to another form. For example, you all know that discrete cosine transformation. We apply the discrete cosine transformation to the input image, and the number of coefficients which uh, come out of this transformation are very, very low. You can say, let's say 50 to 60. So 50 to 60 discrete cosine features are enough for recognizing a person. So in all these figures, which you see are almost similar, but the size of the figure, that is first figure, is 100 times larger than the size of the last figure. It means that the size 100 times size can be easily reduced by using some transformations. But there are several problems also associated with the brain. In the beginning, I also showed that idiot brain, because it is not absolutely intelligent. We can miswrite the brain also, because its working is such that we can hypnotize it. We can
किती का असं आपलं लेक्चर
create
घ्यायचं
illusions for the brain.
नाही नाही एक दोन असं तरी लेक्चर घ्यायचं आपलं आपण येऊन बसते तो सुरू झाल्यावर
Create the confusion between the left and right brain. Actually, when we start using our big brain,
येतात
that
एक
is,
दोन जरी
you
बसलेली
can
असते
say pineal gland, which is even sixth sense. The sixth sense comes from the pineal gland. So, if we are able to activate our pineal gland, so our emotions are controlled, and we actually move towards becoming a superhuman. So we will be able to get information just by intuition. So we will be able to see the colors without opening the eye. We will be able to read the books without opening the eye. So just if we take the book within our hand and close our eyes, and the whole book can be read within, let's say, 5 minutes, if we are able to actually activate our pineal gland. But because of our food habits, generally fluorine scatters around the pineal gland and the communication stops. But if we eat potassium-rich foods, for example, banana, so that actually removes the fluorine chlorides which are accumulated around the pineal gland. So by eating potassium potassium foods, those which are actually having sufficient amount of potassium, so we can easily activate our pineal. People these days are using this type of technique. So another application with where these type of networks or artificial brains are useful. For example, for interpreting the images, whether this image is representing a plane or some balloon or whatever. So if there is a confusion by our brain in interpreting the image, neural networks can help us. So if we show 2-3 images or 2-3 projections of the image, so it can easily develop the 3D model of the image. Our brain is not very capable of doing it. There are some standard models in neural networks which we generally use for research. For example, CNN, which is called which is actually grid-like. If we have a grid-like data, for example, images, we can use CNN, that is convolutional neural network. Convolution, you know, this, what is convolution? If we have two signals and you just reverse the time axis of one signal, and then shift one of the signal and then multiply and add. This operation is called the convolution. So convolution neural networks are able to extract hidden features from the input images. So if you want to find out the hidden features within the images, then CNN network is a very good candidate. Similarly, RNN networks for studying, investigating sequential data. For example, if you want to study this stock market data, then RNN are good candidates. Then generative adversarial networks, that is GAN. These are also useful for studying the data. Then transformers, that is if you want to study the large language models, for example. Large language models, for example, these days, Google is able to understand your language. If you say something, then it is able to type the corresponding text to your speech. So those type of models are called LLM, means large language models. So the recent models which are developed for large language model applications, we can use transformers, then autoencoders, then deep networks, capsule networks, graph neural networks, UNet, and Siamese networks. These are the standard names these days which are generally used for let's say computer vision. Siamese network, that is the network at 10th place, 10th point. Siamese network. Actually, if you want to compare two images, whether they are similar or not, that type of work can be done using Siamese networks. So in our research, also in our lab, we are also using all these type of networks. So different type of network has different capabilities. So for a particular class of problems, one network has been identified, which is used for that. So there are also some pre-trained models. Pre-trained models means there are some models of the neural networks which are already trained by the companies. For example, the first is VGG 16 model uh, uh, and ActionNet. So these are the pre-trained models which are very efficient in recognizing the faces. For example, Google is also using Google Net for recognizing, for identifying the objects. That whenever you upload a picture on the Google, it is able to identify what different objects are contained within that image. So these models are trained using millions of images. So even they are much capable than the human brain these days, because they have been trained using terabytes of data for the recognition of the faces or the boundary lines between the objects, etc. So similarly, another is YOLO. Then NLP, that is NLP means natural language processing. There is also some models, trained model, pre-trained model, that is, for example, BERT. Then image segmentation. For the work of image segmentation, UNet, MAS or CNN are the models which are pre-trained. Then for speech recognition, deep speech, wave to vec is also available, uh, which are pre-trained for speech recognition. Then generative models for images, then style gen, big gen, graph neural networks, graph sage, etc. They are pre-trained models, they are available. You can download the pre-trained model and then fine-tune its working just by training further in your domain. So it is easy to use those models. And here is the mechanism how we do these type of investigations. So, for example, in this case, we take the input image and make it blur, because we want to study how much blurring can be afforded by the machine learning, so its output will not be disturbed to what level of the blurring present in the input images. So here the from the database, that is corpus, images are hashed and they are blurred by different amounts and again stored to the database, and those images are used for training the network. For training, at the first the images are resized, then they are converted to batches, because millions of images cannot be stored in the RAM. They cannot remain in the RAM, because RAM is generally in computer of the size of 8G or 16G, let's say, and generally in our laptop it may be around 4G. So that's why it is not enough. So if we want to investigate using neural networks, so we have to divide our work into batches, divide our images into batches. Sent to the learning network, and those images are sequenced properly and they are given to the learning algorithm, and the learning algorithm actually adjusts its weights repeatedly. So after some time, because when we train the network, we give the input as well as the output. So it randomly selects some weights and calculate the output, and then find out the difference between the actual output and the output given by the network, and according to that difference, that is the difference of the actual output and the, so a time comes and the weights are adjusted optimally, and the output given by the network matches or becomes similar to the actual output, and at the time we say that the network is trained. So now you can use that network for future applications. You can apply any image, so it will be able to evaluate the output corresponding to that image. And if we go further in machine learning, so generally the architecture layers, you can say. So we have convolution layers. Convolution layers, what they do, they extract the features hidden in the input images using some filters, and because the number of features are always very less as compared to the real input image, because always there is some redundant information within the images. So we leave the redundant information and only extract the features from the image, and using convolution neural networks, and those features are again given to the filters and again given to the filters, and at the last we are left with only very few features, very small number of features. Now those can be processed for finding out what type of object they represent. So this is the architecture you can also use. So or actually, if you want to, anyone from you want to work in the field of machine learning. So thank you very much. Any question?
Thank you, sir, for such an informative lecture about machine learning, speech recognition, face recognition, and brain. Any question from the participants?
Request for knowledge.
Anyone like to interact with the speaker can ask.
I think they have understood all the material. So
Yes, yes.
thank you very much.
Thank you very much, sir. Thank you very much, sir, for such an insight. So next lecture is around at 2 o'clock for lecture 3 and lecture 4. So do join at 2 o'clock. Thank you very much.